Welcome to the next lecture on basic laws of thermodynamics part 2. In part 1, we were seeing about work and heat, two topics. We were looking at what is latent heat of vaporization, latent heat of fusion, latent heat of sublimation. We were also looking at specific heat. When we did work, we were trying to understand the formula for isobaric, isochromic, isothermal, then polytropic and enthalpy. So, we were looking into the formulas, how do we calculate the work. Now, let us move to the second law of thermodynamics. So, before we get into the second, we will see the first law, then energy is a property of a system, then first law of thermodynamics limitation, then only you can understand why does the second law come. So, second law, Kelvin-Planck's statement, Cauchy statement, then we studied little bit about reversibility, irreversibility, that we will focus, and finally, we will try to have numerical problems. Friends, all the numerical problems will be dealt in the tutorial session. So, I would request you to use this lecture for understanding, and tutorials we will have 3 or 4 problems which we will solve, and that will be discussed by Dr. Amandeep. The first law of thermodynamics is a statement of conversion of energy principles applied to thermodynamic system. It is stated as energy can neither be created nor be destroyed. It can be only transformed or converted from one form to the another, from mechanical to chemical, chemical to mechanical, mechanical to electrical, electrical to mechanical. See, it is something like that, right? Energy can neither be created nor be destroyed. It can be transferred or converted from one form to another. In thermodynamics, this means that the change in the internal energy of a system is equal to the net heat added to the system minus the work done by the system on its surrounding. Whatever was the first one was very easy, energy conversion. But if you want to put it into thermodynamics fashion, so this is very important. In thermodynamics, this means that the change in the internal energy of a system is equal to the net heat added to the system minus the work done by the system on its surrounding. So, statement 1 is Q is heat transferred, work done. So, this is delta U is equal to delta Q minus work done. So, this is what is thermodynamics first law states. Internal energy change is equal to the heat getting added minus the work done by the system to whom? To the surrounding. In the first law of thermodynamics, the thermodynamics term, it implies that the total energy change of a system equals to the net heat added to the system minus the work done by the system on the surrounding. This law ensures that the energy balance is maintained in all the physical and chemical process. So, you have to understand it is not only physical, it is also for chemical. It forms the basis for energy analysis of thermodynamic system such as engines, refrigerator, compressor and boiler. So, everywhere if you do the energy analysis of a system, we try to use the similar understanding. It introduces the concept of internal energy, a key in thermodynamic property, internal energy. What all are the keywords I have just put? So, if you do not understand what is internal energy, you can go back to my previous lectures and get to know what is it. It explains how much work can be obtained from heat energy, laying the groundwork for technology of steam engine, gas turbine and power plants. So, heat energy. So, the first law explains that how mechanical work, cranking or moving of a shaft, how can mechanical work can be obtained from heat. This is very important. From a boiling of an egg on a pan, lifting the lid gave a seed for the thought of steam engine. So, which started happening at a kitchen in some scientist's house. A pan filled with water, an egg dropped inside, water is boiled from the bottom heat. He could see there was lot of bubbling which was happening, there was lot of steam which was going. This gentleman dropped a lid on top of it, then he could see the lid dancing. So, when the lid dancing, what inference came to him is there is a mass which can be lifted by the steam. So, you look at it, it explained how mechanical work can be obtained from heat energy. That came from the first law of thermodynamics, and that came from the concept of internal energy, right. Everything is fine, but it did not say the last part of it. It shows that while energy is conserved, it does not indicate the quality or usability of energy. It does not say that. So, that led to the concept of, or the seed for second law of thermodynamics. So, the first law of thermodynamics, very simple, whatever example I have given, Q is heat which is adding to the system. Here there is an egg, there is water. So, the heat is transferred to the water, water starts boiling, the egg gets boiled or vegetable gets boiled. So, the pressure keeps on increasing, the volume is constant. After a set period, there will be lot of pressure, the weights will be relaxed and the extra energy will be eased out such that the system maintains the pressure for a given constant volume. So, the first law of thermodynamics says very clearly Q equal to delta E minus W. If you go back to this formula, it is almost the same. The work done by the system on the pressure valve is W. The internal energy is E, or you can represent it as delta U, right. Q is equal to delta U minus W. So, for a closed system, we saw what is an open system, closed system, isolated system. For a closed system undergoing a cycle, the sum of all the work transfer is equal to sum of all the heat transfer. That means to say delta summation of W1, W2, W3 going on to the end Wn. So, I can say going on to Wn, that is a sum of Q1, Q2, Q3 going up to Qn. So, this is represent a summation of W which is equal to summation of Q. So, for a closed system. So, here the integration of W is equal to integration of dQ. For a closed system undergoing a process, this is a cycle. What is a cycle? This is a cycle, right? Rankine cycle, PV diagram, Rankine cycle, Otto cycle, Diesel cycle, Brayton cycle, right? All these cycles are cycles. For a system, closed system undergoing a process, when every heat is absorbed by the system, it increases its internal energy and does some work. So, Q equal to delta E plus W. Whenever heat is absorbed by a system, it increases its internal energy and does some work, where Q is the absorbed heat, W is the work output of the system, and delta E is the change in the stored energy of the system. In some places we have written minus, and in some places plus, and some places we have written minus. So, please think about it and then let me know. So, the energy is a property of a system. So, PV diagram. So, we move from 1 to 2, 2 to 1. So, it is A, B, C, right? 3 paths are there. So, now energy is a property of a system. show that the energy is a property of a system. So, we are just proving it. Path A is equal to QA is nothing but WA plus delta EA. So, this portion, right. Then path B is QB equal to WB plus delta EB. Then when we try to go in this, it is QC is equal to WC plus delta EC. Now, for a cycle 1A, 2B, 1. So, that is nothing but WA plus WB is equal to QA plus QB. So, now moving QA minus WA minus QB minus, you are rearranging the system. So, finally, what you get is in delta EA is equal to minus delta EB. So, now let us assume the cycle path of 1A and C. So, 1A, 2, C, 1. So, that is WA, WC equal to QA, QC. So, now QA, when you rearrange the system, this is what it is. So, now you can compare A and C, which is nothing but EB is equal to EC. Is it clear, friends? So, we are now proving that it is a property of a system. It shows the energy is a property of a system. So, now let us understand the first law of thermodynamics. We try to discuss about enthalpy. It is the energy content of the fluid flow. What is enthalpy? It is the energy content of the fluid flow. It is defined by the summation of internal energy and flow work. So, now we studied two terms which is called as entropy and enthalpy. So, entropy Py, enthalpy is Py, right. So, entropy and enthalpy. So, entropy we know it is S, enthalpy is H. Now, we will try to understand what is this enthalpy. So, it is the energy content of a flowing fluid, enthalpy. It is defined by the summation of internal energy plus flow work, internal energy plus flow work, that is H. For an ideal gas, H equal to U plus PV, PV is nothing but RT. So, H is a function of T. So, if you go into this figure, enthalpy H is nothing but H is equal to U plus PV. So, here is a system surrounding, the heat is applied to an ideal gas. So, to get the increase in the internal energy. So, you can see gas expands to pressure on the piston and creates a new volume. So, defining CV with the help of internal energy and temperature. What is CV? CV is the change in the internal energy, right. The amount of heat, CV, the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius in a reversible constant volume process is CV. CV is defined as a change in the internal energy of a substance per unit change in the temperature at a constant volume is CV, right, constant volume process. So, this is nothing but du by dt. For Cp, which is a constant pressure process, the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius in a reversible constant pressure process, Cp is nothing but delta H by delta T with respect to constant pressure, constant volume. So, the first law of thermodynamics, Cp is also defined as the change of internal energy of a substance per unit change in temperature at a constant pressure. Cp. Cp we saw, Cv we saw. Gamma is nothing but Cp by Cv. What is gamma? Adiabatic process, you can see that, gamma, right. So, now what are the different processes? What are the indices, what they have? What is the Q? What is the W? And what is PVT relationship? You can see all these things in one table. So, for a rev constant volume, so what is reversible constant? reversible constant volume process. What is reversible? Irreversible is already discussed. So, reversible constant volume, the index n is infinite. The Q heat can be written as delta U, which this delta U can be written as m mass into constant volume Cv multiplied by delta T. The work done is going to be 0, and the relationship between P, V and T is given as P1 T1 equal to P2 T2. When we try to talk about reversible constant pressure process, the index n is equal to 0, Q is equal to h. So, that is nothing but m Cp T2 minus T1, where the work is written as W equal to P into V2 minus V1, where P can be written as mR and V2 minus V1 is nothing but T2 minus T1. So, PVT relationship is written as V1 T1 equal to V2 T2. So, P1 by T1, P2 by T2, V1 by T1, V2 by T2, right. Reversible process, isothermal, constant temperature, N equal to 1, Q is equal to W. So, we have PV natural logarithm of V2 by V1. So, when I say Q equal to W, so then what is W is equal to Q, the same formula comes here. So, here P1 V1 equal to P2 V2 when it is isothermal. When it is reverse adiabatic, N equal to gamma, which is nothing but Q equal to 0. So, you see here a constant volume Q equal to delta U, reversible constant pressure Q equal to H, isothermal Q equal to W, isobatic is Q equal to 0. So, Q equal to 0, W equal to P1 V1 minus P2 V2 divided by gamma minus 1. So, that is where the work done. Okay. So, now what is the relationship PVT relationship? P1 V1 gamma equal to P2 V2 gamma. Then which is polytropic when index equal to n, Q is nothing but delta U plus W, where work done is going to be P1 V1 minus P2 V2 n minus. So, this gamma becomes n. It is very easy to remember. So, then this becomes P1 V1 n equal to P2 V2. If you see this, this is very easy to remember. So, when you say isothermal, Q equal to W, right, P1 V1 equal to P2 V2. When you say n equal to gamma, Q is equal to 0. So, W will be P1 V1 minus P2 V2 divided by gamma minus 1. When you put n, it is n minus 1. Both are almost the same. Then, when you go here, it is the PVT diagram is P1 V1 gamma equal to P2 V2 gamma, P1 V1 n equal to P2 V2 n. So, this is straightforward, you can remember. When you talk about constant pressure process and constant volume process, you have a small difficulty. But if you try to talk about the relationship, it is very straightforward. P1 T1, V1 T1. So, when we say constant volume, V is out. When we say constant pressure, P is out from the relationship, right. So, P1 T1, V is out equal to P2 T2. V1 T1 equal to V2 T2, the P is out. So, this is straightforward for you to remember, right. So, now when for a constant volume where n becomes infinite, the work done will be 0. When it is constant volume, the work done is nothing, it is a straight line. So, this is also easy to remember. So, when you do a constant pressure, the Q constant pressure, if you remember constant pressure. So, Q equal to H and you remember this. So, if you want to see, this formula is the only toughest formula for you to remember. Rest all you can easily keep it in mind, right. But all these formulas are very important friends. So, this you have to keep it in mind so that you can solve problems. The first law highlights the energy can enter or leave the system only through a heat transfer or work interaction. It is a universal law that applies to all types of systems, whether it is an open or a closed loop, and the underpin the design and analysis of a machine such as engines, turbines, refrigerator and power plants. So, we have higher temperature reservoir TH. So, you have a refrigerator, we have a lower temperature reservoir TL. So, Q is the energy QL TH, here is the work done. Right? Higher temperature reservoir, which is the ambient temperature, here it is the low temperature. So, Q goes here, work is done on the system. So, when you try to take heat pumps, high temperature reservoir TH is in the top, and here you will have low temperature reservoir TL, which again follows QHTL, and work is done to the system. So, you will have a heat, let it be a heat pump, let us be a refrigerator. So, you will try to have a similar system. So, this applies the first law of thermodynamics. Friends, it will be nice if you could spend little time and see what is heat pump. Heat pump are energy efficient pumps which are used exhaustively today. If you are not able to understand, in the tutorial we will try to cover what are heat pumps. Ultimately, the first law serves as a fundamental energy balance equation and is essential for understanding and designing any thermodynamic system or process. So, this is the first law of thermodynamics. So, for any system and in any process, the first law can be written as Q equal to delta E plus W. For a pure substance, it will become E is equal to Ke plus Kp by U. What is Ke and Kp? Kinetic energy and potential energy. So, Ke is the kinetic energy, Pe is the potential energy of what? Of a pure substance, and U is the residual energy stored in the molecular structure of a system. So, this is how you try to bring the first law of thermodynamics for mathematical solving. So, here Q equal to delta E plus W. Now, we are talking about E. E can be written as Ek plus Ep plus U. So, now you take it there and then you substitute it. Right? So, considering a steam turbine in which a steam enters at a high pressure, does work upon the turbine rotor and then leaves the turbine at a low pressure through the exhaust of the pipe. If a certain mass of steam is considered as a thermodynamic system, then Q is the heat. Q is equal to delta Ek plus delta Ep plus delta U plus work. So, this work is nothing but when you open a tap of water, the water gushes from the tap and you have a very small turbine blade. So, it hits the turbine blade and the turbine blade rotates, or you blow air and then you have a paper windmill. When you blow it, this is a force which is on a tangent and it rotates. So, this rotation is nothing but the work. If you are blowing a steam of very high energy and rotating a turbine, so then what happens when the turbine rotates? There is a shaft. From this shaft you tap out an output. So, that is called the work. So, that is what we say here. In a certain mass of steam is considered as a thermodynamic system, then the energy equation can be written like this. And in order to analyze the expansion process, why is called as expansion? Because in a steam, in a turbine, so what happens? They come with high energy and leave with low energy because they have done the work there. So, in order to analyze the expansion process in turbine, the moving system is to be followed as it travels through the turbine, taking into account the work and the heat whatever is given to the system. This method of analysis is similar to Lagrange's in fluid mechanics. So, it is almost the same. If people want to make an analogy, they can try to make it with Lagrange in fluid mechanics. Although the system approach is quite valid, there is another approach which is found to be highly convenient. Instead of concentrating attention upon a certain quantity of fluid which constitutes a moving system in flow process, attention is focused on a certain fixed region in space called as control volume, through which the moving of a substance happens. So, what we are trying to say is, here is a moving mass, here is a controlled surface, this dabba is a control surface, and what you have in a control surface is a control volume. So, now in order to make it little more easier, we try to always consider a control volume through which the moving is happening. Why is it? Because you know the formulas whatever we saw here, constant volume. So, you can use the problem solving from reality to little bit idealistic condition and try to get the answer. So, this is similar to the analysis of Euler's in fluid mechanics. So, this course is also a combination of thermodynamics and fluid mechanics. So, you will have fluid mechanics where similar concept is also used. To distinguish the two concepts, what are the two concepts? Although the system approach is quite valid, there is an so what is the first approach? The first approach is we try to take the first approach is we try to take a system wherein which we try to put everything in reality. The second thing is we try to consider a dabba. Inside a dabba there is a constant volume, still the same thing is going on. To distinguish the two concepts, it may be noted that while the system boundaries usually changes shape, the position and the orientation relative to the observer, the control volume, boundaries remains fixed and unaltered. Though there is a rotation happening, the boundary which is fixed for the turbine is constant. So, to distinguish the two concepts, the first concept and the second concept. What is the second concept? We have a turbine which is put inside a constant surface, inside a constant surface, constant volume, it rotates. Okay. To distinguish the two concepts, it may be noted that while the system boundaries usually changes the shape, position and orientation relative to the observer, the control volume, boundaries are fixed and unaltered. So, as a fluid flow through a controlled volume, its thermodynamic properties may vary along the space coordinates as well as with respect to time, which is known. This is an important point, please make a note. So, vary with the space coordinate and varies with time. If the rate of flow of mass and energy through the constant surface changes with time, the mass and energy with the controlled volume also changes with time. The rate of flow of mass, whatever steam, mass and energy through the control surface change with time. What is control surface? The external dabba which is drawn here, control surface, right. So, control surface with time, the mass and energy within the control volume also would change with time. There is always a steady flow. The steady flow means the rate of flow of mass and energy across the control surface is constant. The rate of flow of mass and energy across the control surface are constant. In most engineering devices, there is a constant rate of flow of mass and energy through the control surface, and the control volume in course of time attains a steady state. Please try to understand what is steady flow, what is steady state. Steady state means the state is steady or invariant with time is steady state. You know what is a state. Steady flow is the rate of flow of mass and energy across the control surface are constant. So, you know now, and two new concepts I have introduced, steady flow and steady state. So, the steady state means the state is steady or invariant with time is steady state. State, go back to the first few lectures, I have defined what is state. Flow, flow is the rate of flow of mass and energy across the control surface. So, the mass flow rate is m1 and the mass flow rate is m2, which is a constant, we call it as m. Consider a fluid is flowing through a pipe, with a cross section area of A. The specific volume at a velocity c. So, I am trying to tell what is the flow with which a fluid is going. So, I have given the cross section area of a pipe, I have told you what is the discharge q, I have also told what is the velocity with which it is flowing c, right. And now, I wanted to find out the flow rate. Flow rate is nothing but area multiplied by velocity. Rate, when you say flow rate, there has to be something with respect to second. So, that is what comes from here, right. And then I say flow, right. Flow means there has to be a mass and then there has to be in the length scale. So, it is m and length scale is also added. So, this is volume flow rate is A into C and the mass flow rate is m, which is nothing but volume flow rate by specific volume. Okay, that is the mass flow rate. So, from here if we indirectly want to find out m, m is nothing but AC by V is equal to rho AC, which is nothing but a continuity equation. So, here it is P1, V1, U1, C1 flowing through this pipe. Then there is a control system where it is entry is P1, V1, U1, C1, exit is P2, V2, U2, C2, right. This is exit. So, then there is a Q, what happens inside the system? There is a constant surface, which a control surface which is there, right. So, here is W and then this is there. So, datum is the base, right. So, what are we trying to find out? What is this m? So, m is nothing but AC by V, and the mass flow rate is found out by volume flow rate divided by specific volume. Specific volume is per unit volume you are saying, right. So, now the first law of thermodynamics further, if you want to take the notations, the at inlet, at exit, and what are the units. So, if you go back to this problem, so you will see that the entry and exit. So, here are the notations: pressure, specific volume, internal energy, velocity, then elevation from arbitrary datum. That is why in the previous slide I had a datum, right. Then mass flow rate, then cross section of stream, then specific enthalpy. Pressure can be written as P1. So, entry exit will be P1, P2, specific volume will be V1, V2, specific internal energy will be U1, U2, velocity will be C1, C2, arbitrary will be Z1, Z2, mass flow rate will be M1, M2, or it can be M dot. Mass is M, flow rate is M dot, right. M1 equal to M, M2 equal to M. Cross section area will be A1 and then specific enthalpy will be H1, H2. What are the units? Pressure you will have in pascals. So, it can be in megapascals, generally in megapascals, sometimes you can also go to gigapascals. Volume, it is known. So, specific volume will be meter cube by kg. Internal energy U will be in joules per kg. When I say specific, internal energy will be joules. Specific, when I put, it will always be with respect to kg. Velocity will be meters per second. Arbitrary datum height will be in millimeter or meter. Mass flow rate, mass is kg, rate is seconds. So, it is kg per second. Cross section area, when a cross section of stream. So, it is basically area. So, it will be meter square, right. Then the specific enthalpy will be enthalpy. Enthalpy will be joule per kg. So, you should not get confused between enthalpy and internal energy. They have the same units, right. Heat transfer rate of a given system is Q. The work transfer rate is given as W. Heat transfer rate is joules per second. Work transfer is also joules per second. So, when we wrote this first law of thermodynamics, there were not fully straight. There were a lot of assumptions made. Why do you want to know these assumptions? Because these assumptions will give you a lead for second law. Assumption is there is no accumulation or decrease of mass in the control volume at any given time, which never happens. There is no accumulation or decrease of mass. So, the mass changes, that is what they say, in the control volume at any given time. So, that is an assumption. The rate of mass transfer in the inlet and the outlet are equal, which never will happen. There will be losses and there will be friction. The state and the energy of the fluid at inlet and the exit and in the control volume do not vary with time, which is also not true, which varies with time. The state and the energy of the fluid at inlet and exit varies in a constant volume, varies with respect to time. Then the rate of heat and work transfer across the control volume is a constant, which is never happens, right. So, the SFEE on unit time basis, total energy flow rate into the control is equal to total energy flow rate out of the control volume. So, here it is into the control volume, volume is missing. Total energy flow rate into the control volume is equal to total energy flow rate of the constant control, flow rate in, flow out, right. So, this is the same. So, now these are the formulas which are derived out of the first law of thermodynamics. Q plus M is equal to work plus mass, right. So, if you go back to this formula, so we have used all the terminologies. So, Q plus M, which is this, equal to W plus M. So, this is the kinetic energy plus potential energy, right. So, all these things are there. So, where did you get this? Let us see, where did we get this? You see here, okay. Q plus M, whatever it is equal to W plus this. So, when you alter Q minus work done, will be this will be written as this form, in this equation form, right. Enthalpy H is equal to U plus PV. So, now you write it as Q minus W is equal to H is nothing but U plus PV. So, this gets fitted into this, right. M is equal to H2 minus H1 into this equation. So, finally, what we get is this part in the first law of thermodynamics. Q minus W, heat minus work, is equal to mass. Mass M is nothing but the mass. So, into delta H, which is enthalpy, plus kinetic energy plus potential energy. Okay. So, please remember this formula. We are just went around the formulas, right. Let us take a boiler. A boiler is a steady flow device used in power plant to convert liquid water into high pressure steam by supplying external heat. So, this is boiler. You give at some velocity, you send water into the boiler. So, you keep on applying heat to the water. So, then what happens at an elevated time or at an elevated temperature with a long time, all this water is converted into steam and this steam is ejected out through this. So, the boiler is a steady flow device used in power plant to convert liquid water into high pressure steam by supplying heat into the system. So, when it leaves the system, the work is done and then the heat is lost. So, then it comes back and then you again apply heat. It is a key component in the steam power cycle like in Rankine cycle. The working principle is water enters the boiler as a compressed liquid and exits as a saturated or a supersaturated steam. So, it is nothing but take an example of a pressure cooker. You pour water into the pressure cooker and start heating. There is a flow inside, or you pour it inside a standard volume, and over a period of time when you start heating, the water gets converted into steam. That is what we say. The water enters the boiler as a compressed liquid and exits as a saturated or a superheated steam. The heat is added, but no work is done. Heat is only added, but no work is done in a system. So, neglecting pump work and assuming negligible change in the kinetic and potential energy, for a boiler, W is equal to 0, delta KE is equal to 0, delta PE is equal to 0. On this situation, the SFEE equation can be written as Q equal to M H2 minus H1, which is nothing but enthalpy, change in enthalpy. When you try to talk about the condenser, so this is for a boiler. When you try to talk about a condenser is again a steady flow heat exchanger used in steam power plant to condense exhaust steam from turbine into saturated or super cooled liquid water by ejecting heat to a cooling media. So, condenser is condensing. Here what happens? You have a dabba, so there is lot of heat. You eject the heat out. That is what they are saying. A condenser is a steady flow heat exchanger used in steam power plant to condense exhaust steam. So, you get a steam coming inside, steam from the turbine into saturated or super cooled liquid water by ejecting heat to a cooling media. So, cooling media can be air or anything. Purpose is to obtain a low pressure at the turbine exit and improve the cycle efficiency. So, whatever water comes, you eject out the water and then you use it. The working principle is the steam enters as a saturated or slightly supersaturated vapor and exists as a saturated or a subcooled liquid. So, here the heat is removed. There is no work done. So, work 0, Ke is 0, P is 0. So, here Q is nothing but M H1 minus H2. So, if you see previous one, it is H2 minus H1. If you see 1 here, H1 minus H2. But rest all, the only difference is heat is added, heat is rejected. Let us try to take a nozzle. Nozzle is primarily to increase the pressure. When the area reduces, when you are trying to flow fluid through this, when you try to reduce the area, the velocity increases because there has to be a continuity maintained. The nozzle is a steady flow device designed to increase the velocity of a fluid by converting enthalpy into a kinetic energy, H into a kinetic energy, H into a kinetic energy. So, the purpose is accelerated fluid at a very high velocity. So, the working fluid is the fluid enters at a high pressure and low velocity, and exits at a low pressure, high velocity. So, it is used in jet, steam turbines, etc., where W is equal to 0, Q is equal to 0, potential energy is equal to 0. So, the system equation can be written as H1 plus C1 square by 2 is equal to H2 C2 square by 2. So, this is the formula for a nozzle, which is very important. So, when we try to talk about a turbine itself as a full system, turbine is a steady flow device that extracts work from the high pressure fluid by expanding through a series of blades. So, turbine is a steady flow device that extracts work. Turbine itself, something rotates from a high pressure fluid. The fluid which comes inside is high pressure and high temperature. So, steam comes, high pressure fluid, by expanding it through a series of blades. So, to convert the enthalpy, internal energy plus flow enthalpy, which we saw earlier, into a mechanical work is the purpose. The fluid enters at the high pressure and the enthalpy expands through the turbine and exits at a low pressure and enthalpy. So, the fluid enters at high pressure and exits with a low pressure and enthalpy. Enthalpy is there. It is commonly used in aircrafts, hydroelectric stations. So, the formula is nothing but Z1 equal to Z2. This is how we represent Z1 and Z2. So, enthalpy, whatever it is. So, it is derived from the previous formula, C1 square by 2. So, it is only differences. See, you see here Q is equal to 0. So, here what happens? Q is minus and you add W. In the previous one, you never had both the equations. So, the first law has its own limitation. The first law places no restriction on the direction of the process. It does not ensure whether the process is feasible or not. It just derives everything. This law does not differentiate heat and work. So, these are the problem with the first law, and the first law also had so many assumptions. So, these are the assumptions it had. So, I assume this, I assume the fluid is Newtonian, I assume the fluid is ideal. So, all these things were there. Mass flow rate is uniform. So, the rate of mass transfer in the entry and exit is equal. The state and the entry of the fluid at inlet and outlet is the same. The rate of heat and work transfer across the control volume is constant. So, all these things are assumptions. But based on these assumptions, then what is have this? We have also found out certain limitations. It is concerned with the quantity of energy and the transformation of energy from one form to the another with no regard to its quality is one of the biggest limitation. While first law of thermodynamics is a powerful quantitative tool for tracking energy flow, it does not address the direction and the spontaneity of the process nor quality of the energy transform. So, it demands to go for a second law of thermodynamics. And thank you so much.